I'm going to be talking about some work we've done at NCAR on user-driven evaluation of tropical cyclone predictions. And this is work I did, it's with a large group of people, so not all represented here by any means. Louisa Nance is the co-author on the work, and Christopher Williams, who, well, Louisa is the director of the Developmental Testbed Center, a national organization to test modeling and forecasting. Christopher Williams is now studying at the University of Florida Department of Geography, so that he did some great work on this project. So the picture I had on the first slide was something that would be recognizable to anybody who's done work in hurricane, especially this year. This is Hurricane Laura that I think it made landfall on the 27th of August. So this picture is just before it made landfall, and it was the 10th strongest U.S. hurricane landfall on record, which led to a bunch of deaths and a huge amount of damage. And so a lot of that potentially was related to the intensity of this storm, a lot of that damage. So predictions of tropical cyclone track and intensity are very important for planning evacuations, protecting life and property, and so on, as all of you know. The goal of this presentation, though, is to consider user-relevant, meaningful ways of evaluating NWP guidance to aid forecasters in making the kinds of predictions that they made for this forecast for this storm as well as other storms. So I'm going to present a simplified version of the value chain that Beth showed just a few minutes ago, which is one that was developed by Jeff Lazo a number of years ago. And the reason I'm showing it is I think I want to make a point that there are a few things that there's some spaces. I think there's more complexity in each of these boxes, undoubtedly, than what is shown here. And the complexity I want to talk about a little bit is in the modeling and forecast part. In particular, what we're talking about in this particular project is the NWP and OBS that go to forecasters, and then forecasters make decisions about their forecasts and their warnings. And that's exactly what happens at NHC. That the forecasters get lots of information from the initial steps, but then they do their work and create the warnings and the forecasts. So this study considers the question of how verification information can best inform and facilitate the use of NWP guidance by forecasters. So that's our goal, is to look at this little bit of the value chain, this extended value chain. So the idea of user-relevant verification has been around for a long time. We published a paper back in 2008 that Rebecca Morse was the lead author on, where it appeared. And then it's also in a paper that we put together that Beth was the main author on, that was published in METZ in 2018. So I'm not going to go through all the details of this because we could spend a lot of time on each of these levels and argue about whether they make sense or not. But what I'm going to be presenting today is what I would call a sort of level 3 activity, where we're looking at user-relevant verification approaches and measures. And another way to think about these is that they are actually user-driven, particularly in this specific example that I'm going to be describing. So we're not quite with this getting to the level of actually estimating the value of forecasts by looking at the economic impacts of decisions, or economic or human impacts of the decisions. But we are defining verification approaches based on what the needs are, the specific needs are of a set of users. So as I just said, the idea of user-driven or user-relevant verification approaches is that they consider information needs of specific users rather than applying a standard, a one-size-fits-all approach to all forecasts So for example, the common use of the mean squared error or anomaly correlation for NWP might not be adequate to give the right information, for example, to hurricane forecasters or tropical cyclone forecasters. And these approaches, in order to develop them or identify them, require an understanding of what the user's questions are about the quality of the forecast, so that we can define measures that answer those specific questions. So just a little bit about the project that was the driver for the work that I'm going to describe here. Is the Hurricane Forecast Improvement Project, which is an ongoing project. It was initiated in 2007 to try to significantly improve forecasts of tropical cyclone position and intensity predictions. Those were the initial goals. And initially, we wanted to be able to demonstrate significant improvements in predicted track and intensity. And I bolded intensity there because I'm only going to present some description of methods that we developed for intensity, evaluation of intensity predictions. You can see on the right-hand side there a diagram that shows intensity forecasts for a particular tropical cyclone. I don't even remember what storm this was, but you can see a variety of model-based forecasts of how intense the storm was going to get over the forecast period. You can also see the best track in the black, which is what the Hurricane Center forecasters predicted. And you can also see in the black dashed lines what the actual best track was. So the best estimate of what actually happened. So you can see these forecasts were pretty far off in terms of how this system actually evolved. So the goal of the NCAR project was to provide guidance to the National Hurricane Center, or NHC, to help them select experimental models that operational forecasters could look at during each tropical cyclone season during this project. And so basically, the HFIP project funded a lot of different modeling groups to try to improve the NWP that was available for the forecasters to look at. So each year, NHC wanted to check out these models to make sure that to choose the ones that seemed to be most promising and that also wouldn't degrade the information that was available to the forecasters. So one of the goals was to select models that would do no harm. So we didn't want to give the forecasters information or put information in front of them that was pretty clearly not going to be useful or could be even negatively useful. So the approach to this project it evolved over time. So each year, I think we did the project for 7 years, did these evaluations. And the approach was to work with NHC staff to identify questions that were relevant for their use operationally, for use of these models, and then to develop verification approaches that would answer those questions. And the goal was to compare the experimental model performance to the performance of some baseline models, which were modeling systems that NHC was already using and had confidence in, or some confidence in anyway, enough confidence so that they were using them and referring to them. And each year, the forecasters, the modeling groups, produced 3 years of retrospective forecasts. And we also had baseline forecasts for those also the same 3 years. The models were evaluated each spring before the start of the hurricane season. And then the models that were chosen that satisfied the criteria ended up being demonstrated to the forecasters during that next hurricane season. So some of the questions that we asked as this project evolved, and we worked with the managers and the forecasters, were things like, does the experimental forecasting system perform as well or better on average than the baseline models? Does the experimental system have more or less outlier events? And how does the candidate model rank with the baseline models? So is it much better, much worse? Does it consistently have some rank within the other models? And those are some examples. We did the project was actually a little broader than that, but these are the things that I'm going to talk about now. So the next few slides will show some examples of results for a single candidate model, what we call an experimental model, and its predictions of TC intensity in comparison to two baseline models. So the first question that we were interested in asking, as I mentioned, was whether the candidate model, which we call E1, have smaller errors than the baseline models, or at least no worse errors than the baseline models. And here we're calling the two baseline models that we're looking at B1 and B2, so baseline 1 and baseline 2. And what I'm showing here is the traditional intensity verification that I think is still done at NHC and by others, looking at average intensity errors as a function of lead time. So we see in black the B1 on the left-hand side, B1 versus E1. E1 is in orange. And on the right, B2 versus E1, where again, E1 is in orange. And you can see that it looks like in both cases, the experimental model performed better than the baseline model, although the error difference was not much smaller in the comparison between E1 and B2. So it looks like, you know, pretty good. If this were all we were going to look at, we would say, yes, go for it. This experimental model is great. But if we actually consider the uncertainty in those verification results and put confidence intervals on them, we get a much different story. So let's just look for now at the orange and black lines at the top. And you can see that there are confidence intervals on each point. And you can see that there's overlap between the black and the orange lines, which suggests that none of the differences are statistically significant. So that's true for both comparison B1 and B2. So that contradicts the results that we saw in the previous slide. But if we do pairwise comparisons, as shown in the blue lines, where we've put confidence intervals on the pairwise differences between the forecast errors at each time, we find significant differences for most lead times relative to baseline 1, but only significant differences for some lead times for baseline 2. So it's quite a different story than you get by these intermediate approaches. So another question that was of great interest to the forecasters and to the managers was avoidance of whether there were going to be more busts with the baseline, with the experimental model than with the baseline model. So we define busts as having significantly large errors with the forecast. And you can see if we look at baseline 1, we definitely are seeing more errors with the baseline model than with the experimental model. So in this comparison, the experimental model seems to be greatly improving the performance. And whereas on the other hand, if we look at baseline 2 versus the experimental model, we don't see the same kinds of large errors or differences in large errors than we did with baseline 1. So it definitely seems to improve greatly in this regard over baseline 1, but not so much over baseline 2. So the forecasters were also interested in what is the frequency of, let's see if I can go back here. How frequently were the errors large for the experimental model relative to the baseline models? And so what this diagram is showing is the frequency of cases where baseline model was better than the experimental model, or the experimental model was better than the baseline. And so these have confidence intervals. These are 95% confidence intervals for the question of errors smaller by at least five knots. And so you can see for most lead times, particularly after 48 hours, that the frequency of large errors was much smaller for the experimental model than for the baseline model. I forgot to mention that the gray line shows where there was a tie, and so there's significant improvement by the experimental model over the baseline model here, which gives confidence that overall, in general, the experimental model is going to do okay. If we look at baseline 2, we get a little bit different story because there are lots and lots of ties, which suggests that the baseline model and the experimental model essentially performed very similarly to each other. But in those cases where they weren't tied, in general, the experimental model did better than the baseline model. So these kinds of results give confidence that E1 is probably not a bad forecasting system to look at. And finally, we looked at how the experimental model ranked in comparison to 3 baseline models. So I've added a third one in here. So there are four models that we're comparing, E1 plus baseline 1, 2, and 3. And so this diagram is showing the percent of cases where the experimental model ranked best, or second best, or third best, or worst. And so we don't have a criteria for how much better, but if the errors are smaller by some amount, then it's counted as better. And what we see here is that for some lead times, it was second best. The experimental model was second best significantly. Again, we've got confidence intervals around these ratios. And then, so for those shorter lead times, it was often second best. And for the longest lead times, it seemed to be performing better than all 3 of the other baseline models. And I think a useful piece of information is how often was the model the worst among the 4. And here it suggests that it's something less than 20% of the cases the experimental model was the worst. So some conclusions from this is that it's really important to look at the uncertainty in these verification measures, especially if we're trying to influence decisions. That makes these decisions more defensible. Evaluating user-driven questions gives us strategies to make rational choices about which forecasting system should be used for particular applications. I think this is not unique to this particular study, but is a broad kind of idea that I think is worth following up on for other kinds of projects. And then simple or standard questions that we frequently ask, such as about average behavior, may not meet what the user needs are. So developing user-driven approaches that involve really working closely with decision makers really are important. And I think for high impact weather, that's really important. And for the whole idea of the value chain, thinking about user-driven approaches to get this kind of information. It takes a lot of work, but I think it's worthwhile. The approach here was, I think, could be a model for other kinds of applications like this as a component of the value chain. So that's all I have, except to give some thanks to many people who contributed to this, in particular the forecasters and managers at the Hurricane Center who took great interest in helping us with this and identifying the information that was important. So, and also the HFIP project office and the modeling groups who continuously put a lot of effort into providing their forecasts to us. So that's all I have. Thank you very much, and I'll take any questions.
Hi, Barbara. We have a question from Brian Golding.
Okay.
He says, am I right in thinking that your metric for intensity is maximum wind speed? In light of recent published research suggesting that total damage is poorly correlated with maximum wind speed, are you planning on looking at other metrics of intensity, such as central pressure, which may be better correlated with damage?
We're not actually doing this project anymore. But I agree with you, Brian, that would be a good idea. And I think there probably are other kinds of other factors that should be considered too, besides just the intensity. As we've seen a lot of damage in recent years from precipitation. But that was there had been such a lack of improvement in intensity forecasts that that's why HFIP decided to focus on that.
I have a sort of related question. Do you ever run a damage model itself, with the truth sort of analysis and then sort of verify the actual damage like that? Can you do something like that?
I don't see why not. Yeah, but we have not done that. This really just stopped with the forecasters.
Okay. So we have another question from Tom Robinson. The errors for the E1 and B2 were flat from about 48 hours on. Is this typical of intensity forecasts? And if so, why is that? Why don't we see an increase in error with lead time?
And I don't have a good answer for that. I think if there's somebody on the chat who has some more experience with hurricane forecasts, they might have hurricane forecasting. They might have that some ideas on that. I'm sorry.
Mm-hmm. I don't know how we're doing for time. There's a couple more questions here. In fact, 3. Marianne Giraud, does that mean that you see that you should use operationally different models on different lead times?
It's possible if there was a strong enough signal that you should. I think our goal was really to show that overall the forecast didn't show an overall degradation. So I think that would be another kind of question that could be asked in the value chain work is, is that something that should happen? And I don't have an answer right now, but you could if you had that ability and if there was enough consistency between the models so you weren't jumping around a lot. That's something we haven't evaluated is consistency in the forecasts, which is also another factor that people and forecasters are concerned about. It's possible that changing models for different lead times would make sense. I mean, we already do that, moving from mesoscale models to global models and so on for different lead times.
And then sort of following on from that, Michael Foley has a question. He sort of says that tropical cyclone forecasting typically uses the model consensus approach. So did you do any evaluation of the extent to which the new model improved on the quality of the consensus forecast?
Yes, there was some work done with the consensus forecasts. And I don't have results on that, but yeah, I think that would be one way that you get away from that issue of the switching back and forth between models. Often you can get away from the jaggedness of that kind of switching if you look at a consensus, or even the jaggedness within a particular model if it's not being consistent from time to time. So it's again, what is the important factor that you're looking for? Is it consistency from time to time, or is it getting overall the best forecasts across all times? So it's tricky business, I think, and that's another thing that I think would be a good thing to evaluate as part of some of the work on the value chain.
So I just want to stop me if we're running out of time, but there's a couple more questions.
Maybe one more question, if that's all right, Mark.
Okay. So the next one is from Darren Griffiths. Operational forecasters can't look at an unlimited number of models. In the examples you showed, it looks like they should add E1 and possibly stop using B1. Having E1 and B2 of similar standards seems more useful than just one of them. Any comments?
I think that the ultimate goal of the project was to select characteristics of models that would go into a system that would overall provide the best forecast, and then you would probably not have to be looking at as many models. So I know the forecasters are always going to want to look at more than one model, but it was mainly to try to improve the operational systems in general.
Okay, Brian Golding just gives a possible answer for why the errors don't increase with lead time, thinking that things may be saturated, errors may be saturated. But I guess you could reply to him later. Okay, yes. So that's it.
Okay, thank you, Mark.
Okay, thank you very much, Barb. That was great. So now